Okay, sorry about that, guys. Let's get back to it. So, oh my goodness. There we go. Okay, so a weighted graph, once again, is just a network where the edges have weights, or they have a number on it. We call that the weight of the edge. Generally, this is where networks are used in real life, planning, etc. So they have numerical information on each edge. These are called weights. And if I said, okay, I want you to go from 1 to 2 to 4, the total weight of that walk would be 6. So the total weight from 1 to 2 to 5 would be 6, because there's 2 to get from 1 to 2, and then 4 to get from 2 to 5. So altogether, it would add up to 6. Pretty straightforward, right? What we're going to be looking at today is I'm just going to give you a bunch of different graphs, and I'll say, okay, get from like 1 to 3 in the shortest distance possible. And that's what we're going to do for the first half of today. The second half will be that Eulerian stuff, which we'll get to. Okay, so guys, what's the weight of the edge between vertex 2 and 3? Yeah, 14. And can you calculate the total weight of the walk 2 to 4 to 1 to 2 to 4? So probably do that one in your book. Just calculate the total weight of the walk 2 to 4 to 1 to 2 to 4. Huh? Oh, sorry. I was thinking about my last class. I got to call home for some behavior. I now realise people were talking to me. I apologise. No one was. I thought someone said something. I'm just waiting for you guys to like do it. That's all.
I did.
Oh. Okay. So what was our total weight? Oh my goodness. 17.
17 unknown units.
Did you really?
Yeah, we're like 17.
Oh my goodness. Oh wow.
So, you want us to take
Okay, Ty. It's okay, Ty.
Okay. I think I'm back on this planet. I apologize, guys. So from 2 to 4 is 5. Then 4 to 1 is another 5. So that brings up to 10. 1 to 2 is 2. So that gives us 12. And then 2 to 4 is 5 again. So that's 17. Whew. Okay, so shortest path problems, guys. They involve finding the shortest path from one vertex to another. You don't need to go to every vertex or anything. You just need to get there as quickly as possible. So in terms of real life stuff, this is saying, okay, I have, I need to run electricity from the central power station to like all the different towns. Is it going to be easier to run power lines from the central thing to each town individually? Or would maybe you go from the central power line to town A and then from town A to town B instead of going from central to town B? So that's what we're going to look at doing. Okay. So the length of the shortest path is just the sum of the weights for every edge that it covers. Using trial and error to solve. So that's important. There are mathematical ways to prove that something is the shortest way, but we don't do it at this level. So we just use trial and error. So generally there'll be an obvious shortest path.
So you're recording that whole thing, eh?
Yeah.
It's like 17, you're like...
Anyway, so we only need to use trial and error. We don't need to worry about anything there. So basically you just want to try and find the edges with the smallest weights that get you to where you're going. So let's have a look. I want you guys to find me the shortest path from 1 to 5 and the shortest path from 3 to 5. So can I get you to draw that one in your books? Why is that?
So is it like one with the less weighting or just...
Well, what is the weighting? Yeah, but like when you say the shortest distance, what do you mean? Do you mean if you got like a ruler and measured?
Say 3, right? 3 to 5.
Yeah.
Just go from 3 to 5, you go 3 to 2 to 5. 5, yeah, 3 to 5. That's right.
Which is what you want.
So is that what we're trying to find?
Yeah.
So from 3 to 5, going that way, you know, if we're talking about how it maybe costs $34,000. So lay like cable from 3 to 5, really costs $14,000 from 3 to 2 and only $4,000 from 2 to 5. So if you had to get like a piece of shit and then it would be easier to go on that road. Or if you're driving from town 3 to town 2, it's 14 minutes. There's not 4 minutes from 2 So that's the way you'd rather go. Maybe you have to like push back down some like dodgy roads to get to the right between.
It's quite fun.
Alright. For some reason it's not letting me draw on the screen today, which is very annoying. Okay, so shortest path from 1 to 5. 1 to 2 to 5. Yeah, there's literally nothing that really comes close to that. Going 4 to 5 takes forever. So yeah. So it has a total weighting of 6 from 1 to 5, taking the shortest path. Shortest path from 3 to 5 would be what? 3, yeah, literally 3, 2, 5. And what would the weighting of that one be? 18? Okay, let's have a look at this one. So this is a bit more realistic in when you'd see this problem. And you might remember as well, guys, when we first started talking about networks, I talked about how your GPS works. And this is actually the way your GPS calculates where you should go. So your GPS, every intersection, it like maps out as a vertex in a network. And it uses data from how long it takes to go between individual places. And then if you say, I'm going from Bowen to Townsville, it will find the shortest path based on times to get you there. And that's why it'll do what it does. Which is quite funny because if you've ever driven from Bowen to Townsville with GPS on, or like the Google Maps GPS, it avoids air by going through like these single lane like highways through cane fields. It's super weird.
That's why everyone.
I hate it.
Cool. You only go through air for one KFC.
True. I always go through air, but I never get KFC there. No, well, like, this is beside the point, but a KFC should have a drive-through. It does.
It does.
In air, really? Ah. I always assumed it didn't. I thought you just had to like park out the front and walk in like a scrub.
You smell that? Privilege.
Anyway, let's not get too hung up on KFC. So guys, the graph below shows 6 towns represented by vertices and the roads between those towns represented by edges. So the weights on each of the edges show the travel time. So between Chilcon and Dinkle is 10 minutes, Dinkle and Finton is 50 minutes, Everidge and Dinkle is 20 minutes, etc. So find the total time it takes to travel the shortest path from Armadale to Finton. So we want to start at the very left, end up at the very right. 70? I think 70 is correct. There's not really... guys, I'll just talk you through my logic when I do these. I just look at where I'm starting, Armadale, and then look at where I want to get to, Finton. Now, straight away, would I rather go down the 60-minute path or the 20-minute path? 20. So it's taking me 20 minutes to get to here. Now, would I rather go down the 20 or the 30? Or the 20 gets me there, and then it's going to take another 30 to get to Finton. So 40 minutes plus 30 is 70 minutes. And there's not really any point, like, at Brooks, I could have taken this 30-minute detour, but then it would have been 50 minutes to Finton. So it's not worth doing. So 20, 20, 30, 70. Oops. There you go. So the shortest path from A to F is A to B, B to E, E to F. 70 minutes. There you go. What I'm going to get you guys to do is page 426, question 1 to 4. We're only going to give you like, I think I might give you 10 minutes. It's not too hard. Yes, Lily. I suppose so.
Ouch.
Oh, now I don't want it, but I'm gonna.
Name that movie.
I assume with you two, it's probably Step Brothers.
Nah, Anchorman.
Like next to the door.
Great movie. Have you seen it?
I actually, when it came out, I went and watched a double feature of the original Anchorman and then Anchorman 2 at the movies. Really? Huh. Does anyone need a textbook?
Millennials. If he hits me, I will hit him. How the world works. Wait, we love that.
So just question 1 to 4, guys. Shouldn't take you too long.
It is leave my lovely, but it's like it's my phone.
You have a password.
I have a password that's easiest.
It's like a 11111. Why even have a password?
No, because I just want to
You just want to pay.
Alright. I'm being nice. I'm giving you 12 minutes, guys. 12. I'm giving you 2 extra minutes. These ones are pretty, like, I don't expect you to redraw the graph or anything, so most of it is counting. Pretty sure you guys do alright at that past preschool.
Is there any cure for like mosquito bites?
Like,
You just leave them and they'll eventually go away.
if you spray insect repellent on it, mostly they have something in it that soothes it.
Or my head.
It's like them everywhere.
You know what you should absolutely do?
No, I already did it, so we're good, actually.
But, no, not really. Suppose maybe if you died, then you're not going to feel it anymore. But aside from that,
So you go from B to D.
yeah. C,
Well,
F. You have to go through B though to get there.
Generic.
Question, guys. When I was zoned out, how long was that for?
From about 2 minutes.
Oh god, that's worrying.
Is that?
That's not too worrying, I guess.
I mean, it is that
What
like.
if we all just got up and left? And you were just like, we just screamed, wake up!
We'll walk past and you can
No. I'd like to finish in 12.
Yeah, that's a bit.
1 to 4, mate.
Jeez, mate. Which tutor?
Why? Why don't you have yours? C to D by B. Simple maths. So after I finish this question, can I quickly go to the bathroom? Thanks. Get my calculator. So visit every town. On the shortest time.
What's our timer up to? 8.5 minutes
Left or
left.
okay. Gonna say yikes.
You said, really? You sound like you like.
Name numerical units I can use. Find the length of the shortest possible.
But I could be, no, I should.
Wait, you did D. What's D?
Find the shortest time to start at 8 minutes with every town.
Oh. Every time. It's literally just 8 minutes.
Guys, anyone not up to question 2 or 3 yet?
Don't forget.
1543, actually 76.
We have to look at the. I just did whatever I thought. I didn't do separate rooms.
I just did my first one.
Guys, about 5 minutes left. Our goal is to get all 4 of those questions done. You guys, 3 minutes left.
Yeah.
What was your answer before? It's 19. I think you might have gone to the wrong. You might have gone to the shortest path. Like there's 2 paths of quests.
11, 3, 3, 2. Yeah.
Another question.
Yeah.
Another question also, you found the shortest date. This will be 19. Yeah.
Hey, Evelyn.
Yeah, I mean,
It's weird.
The buttons. Yeah, they have to go budgie cut somewhere else. That's good, Dave.
Okay, ladies and gents, we might leave that there. That's about as hard as those questions get. You just need to make real sure that you're looking at all your options when you're doing those weighted ones. So what we're going to look at is Eulerian and semi-Eulerian graphs. So, Eulerian trails, I should say.
What were the ones we just did?
Weighted graphs. Weighted graphs and shortest path problems. Okay, so an Eulerian trail, let's imagine you are a national park ranger. You're in your little, I don't know what they drive.
Buggies.
No, not in a national. They'd have like a Land Cruiser. You're in your little, or maybe a Jeep. You're in your 4-wheel drive. You got your hat on, and you're like, you know what? Today I'm gonna check out all the roads in my national park. Now, ideally, if that's your job for the day, you don't want to be repeating effort. So if you're checking that everything's all right along all the roads, you don't want to be going over the same road twice. So a park ranger might need to travel along each of these roads in order to check their condition. It is the best interest of the park ranger to minimalize the number of times each road is traveled and avoid backtracking when possible. Ideally, each road should be traveled only once. So traveling every edge in a network only once is called an Eulerian trail. And the possibility of one occurring depends on, we're going to write the bottom one down. The possibility of one occurring depends on the degree of the vertices.
The last one.
The last bit. So I don't care about the national park guy. I just want you to think the actual definition of the Eulerian trail.
versus.
If you've got that down, just have a look up there at that graph that I've drawn, and see if you can find an Eulerian trail through it. So a way you can go around so that you only get each edge once. Found it?
7.
Like one of those ones. Do we have any tissue?
And then try that one. Yeah, because it's a trail, you can use the same vertices.
Done.
Done, you reckon?
I think so.
Well, I think we all have that down now. Let's have a look. I'll just go through an example of the first one quickly. Let's say I start, I'm going to choose a random place. I start there, and I go along that one, then 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 oh no, I put myself into a corner. Can't do it that way. This one is definitely solvable. I just did it the wrong way. That's all. Okay. Let's go that one, then that one. Then I'll go to there, then to there, then to there, then to... No, I've done it again. I'm trying to be too fancy. You can do that one. Oh. Whoops. So I'll go from there to there, to there, to there, to there, to there, to there. Okay, yep. That one I actually made harder than I meant to. But that one is solvable. This one should not be. Possibly. Do you want to show us what you... how you did it? Because it shouldn't be solvable.
I need to remember now. Because I probably did this right. Just do it 3 more.
I think you missed one of these cross ones.
Use the cross.
Yeah, you haven't used that cross.
Yeah, I probably can't use it.
Yeah.
I must have just forgotten.
And that's what this second dot point sort of says, is I can make them so that they're either solvable or not solvable. It depends on the degree of the vertices. With this one, can you see that I have degree of my vertex 2, 3, 3, 3, 3. This one has degree 2, 4, 3, 3, 4. Basically, the way these ones work, if you have everything having an even degree, it's an Eulerian trail. And what that means is you can start anywhere on the graph and make a Eulerian trail out of it. This one, you see it was solvable, but it has odd vertices. If it doesn't have all even, it's allowed to have one pair of odd vertices. So I've got these 2 3s. And that means you have to start at one and end up at the other one. So that's called semi-Eulerian, and we'll have a look at that in a moment. That's the one we just did. So, if the degree of every vertex in the graph was even, then the ranger could begin at any campsite, travel along every road once, and end back at the beginning, so back where they started. A closed trail that involves every edge of the graph can be called an Eulerian trail. A graph that contains an Eulerian trail is an Eulerian graph. A graph is Eulerian by definition if all of the vertices in that graph have even degree. I'm not going to get you to write that all down. Can I get you to just get the blue down, please? We go on to semi-Eulerian. So this is Eulerian. If everything has an even degree, then it is always possible to start at any vertex and travel through every edge once. You may need to reuse some vertices, but that's fine. And you'll end up where you started. And that is called a closed Eulerian trail. And if it has a closed Eulerian trail, it's an Eulerian graph. Getting this down, boys?
Oh, crap, sir.
Zoning out worse than I was.
Yeah.
Yeah, let's think of something else.
So what we run down to?
The blue. Yeah,
What?
what?
You got a funny story to tell now, though. That you zoned out.
Oh. I thought you said I thought you said you have a funny story to tell. So it's like, well, that's a strange thing to.
You,
Yeah, but I heard it as I. Yeah, you know.
you still zoned it out.
It's not that. Not that. Funny jokes.
Oh.
Cool.
Dude. Yeah.
Well, one pair did. One other one. Oh,
I feel like
it's confusing there. But one of mine.
He's doing it again.
No, I'm just waiting for you guys to be done so we can move on. You're an absolute pest, Eulerian. An absolute pest.
I'm gonna get you a mug that says absolute best.
You should get that mug for Lillian.
No, he said. Here's the real test. That's why we get you.
You got me.
It wasn't me, bro.
Oh.
Okay. Almost done, guys.
Yep.
Actually, still going. Casey and Casey still going. Oh, goodness.
You sleep yesterday?
Yeah, I got
I slept during the day.
but I left it so late. I should have slept during the day.
I slept during the day and night, so I'm a little bit.
You good, Casey? Or you still going?
I got like 5 letters to go, so I'm sorry.
Unacceptable. Oh, okay, to the space.
Hey, Blake, jeez.
To the try.
It's not usually the way.
Okay, so guys, a graph like this.
But we just took that footy with it. And then.
Psych.
So hate sleeping
1,
on
2, 3,
sand.
4. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. Okay, so guys, this graph that I just drew, degree 4, degree 4, degree 2, degree 4, degree 4, degree 2. So I challenge you that you'd be able to start anywhere on that graph at any vertex, go in, and you should be able to make a path so that you use every edge once. Willie?
So we did one of these on our exam and it had odd degrees. Can we just go through and count the degrees, and if it's odd, then we just don't work it out, or should we still try and work it out?
If I gave you an exam, I think there's an example on the practice mock exam, for example, where it says, is this graph Eulerian or semi-Eulerian? And if you look at it, it has like 2 odd numbered degrees, which makes it semi-Eulerian. So all you need to do is count up the vertices and say, well, there's 2 odd vertices, so it must be semi-Eulerian. And you don't need to go work it out. And as well, if it had 3 odd degrees, you could just say, well, there's 3 odd degrees, so it can't be any type of Eulerian graph. I don't know. Well, I'll start at this 2, and I'll go there. Then I'll go there, 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 there. Then I'll go there, to there, and there, then there, and then there. And then I'll finish off there. So you start at a vertex, you have to end up at that same vertex. So I just managed to do that. Okay, so guys, that's Eulerian. The other option, semi-Eulerian. So if there's 2 odd vertices in the graphs, the ranger can only start at either one of those campsites. So I think that's what you're thinking of, Nathan. So if there's 2 odd vertices in the graph, the ranger can only start at either one of them, travel along every road only once, and they don't end up where they started. They end up at the other odd degree. So it's an open trail that involves every edge of the graph. So a graph where an open trail exists that involves every edge without repetition is a semi-Eulerian graph. A graph is semi-Eulerian if it contains exactly 2 vertices that have odd degrees and all other vertices with even degrees. So the sort of cliff notes of it, guys, is if there's all even degrees, it's Eulerian. If it's all even degrees bar 2, it's semi-Eulerian. Otherwise, it's nothing. It ain't special.
And for the semi-Eulerian, you have to start at one odd one and end at one odd one.
Yeah. Yeah, and the semi is the open one, and it has to have 2 odd numbered vertices. Sorry? Then if it has more odd numbers, it will be closed. Like you won't be able to draw an odd number one. You won't make it. Before.
No, when you said it wasn't.
No, you said it was only 6.
Say again.
I said if you have 8 and 5, because if you said it was
Yeah.
Okay.
No, so if it has all odd numbers, it will be possible to start at any point.
I'm getting tired.
Every
I'm really hungry.
I'm tired, I'm sick of your shit.
Essentially, every, you know how like we'll talk about the handshake where every edge adds 2 to the degree. If you imagine that everything is even, so everything has an even number of vertices, edges out of it, kind of
Because I did not.
there's pairs of like entries and exits. So and if everything is even, for each entry there's an exit. So you can just sort of keep bouncing around the graph until you get back to it.
Good luck.
Okay, ladies and gents, we've got about 10 minutes left. 10 minutes left. I don't want to leave this till Thursday because I don't want you to forget it. Can I get you to have a go at page 418, question 1 and 2? It's just about Eulerian stuff. So you just need to identify in question 1 what's Eulerian or semi-Eulerian and what's not. And then for question 2, it's a semi-Eulerian graph. You just got to answer a couple of questions about. So can we do that one?
Yes. It's the one. It's that one there. So then.
Yeah.
We've only got about 5 minutes, guys. So, but just try and do question 1 today. Finish off question 2 before Thursday, though.
No, it's not.
B's not. Yeah, there's more than 2.
There's 2 odds. More. 2 pairs of odds. So no, it's
Neither.
I'm just really hungry. Yeah, I got.
Well, this counts as 2, right?
Yeah, that's 1,
Yeah.
2, 3, 4. Yeah. 1, 2, 1, 2. Yeah, no, that's 7. That's 7. 1, 1. I thought.
Oh, you're right, yeah.
Cheeseburger identification. 2, 2, 3. No, that's 4. 2, 2, 4, 2.
First one, that'd be semi-Eulerian. So for that one, it's got
That's
2.
3 ones.
No, that's 2. They're all similar.
It's got 2 odd number vertices. Yeah, so because it's got 2 odd number vertices.
Name any
it's
open and closed Eulerian trails.
If it was
Still right, gay.
Closed.
say again.
Closed.
Yeah, so that is
Closed. It's not
Eulerian or semi-Eulerian because you have a maximum of 2. And you can't have 1 odd number vertex.
So say D, E, and C are
Yeah, the last one's just pretty Eulerian because everything's even. So middle one not Eulerian, left one semi, right
So
one
A-
Eulerian.
A and B is closed.
No, B is nothing. It's not.
Okay, so it's just A.
Name any
A is
open,
closed, C is
closed,
open,
vertices.
E is closed, E is open. Each same breed. Don't mind.
Yeah, really hard to. Really hard.
That's why when I make my sandwich again, where it's like
So.
it's
Uh-huh.
it's white bread and then it's
They all,
No.
every vertex has to have an even
white
degree.
and then wholemeal.
You
And I'm like,
want, you just want the one type.